Ladies and gentlemen, boys and girls, welcome to our final recitation. Today we're going to be going over this guy right here. We got a couple problems to look at, and this should be fine. Alrighty, so if you want to, take a minute to pause the video and kind of see how you would do it. But these are our problems that we're going to go over, and let's just make it happen. So we're going to start with problem 1 here, right? We got x e to the y. Well, you guys had the problem, so I assume that you guys have it copied somewhere. But so we're going to have, f is given, and we want to find the integral of the curl. So let's integrate over s f dot ds, right? And we know that this is inside a sphere, so this is going to be equal to the triple integral over our, how do we want to call this? S is the sphere, which means that this is going to be the ball. Right, so it's the ball that, it's going to be that 3D shape. Where x squared plus y squared plus z squared is less than or equal to 4. We're going to integrate over this ball, and it'll be the divergence of f. Now, is this good? Well, we have to keep in mind this is going to be a negative. And the reason, so this is like divergence theorem. And this negative comes from the fact that it's inward, right? Divergence theorem, we need our surface, we need it to be oriented outward. So because it's oriented inward, we just put a negative there. Okay. Now, what is the divergence? Well, if we compute this, x plus e to the y, this will be the integral negative ball. The integral of 1 plus 1 dv, which is just negative 3 integral over the ball dv. Right, and then what is this guy going to be? Well, this integral here is just negative 3, and then we've got 4/3 pi r squared. Our radius here is 2. And so this is going to be negative 16 pi. Right? Oh, cubed. Sorry, wait, I'm tripping. This is cubed. This should be negative 32. Erase this. This guy here will be negative 32. And now I think we're fine. This 3 cancels. We have 4 times 2 to the 3rd, which is 8. And okay, perfect. This is how we would do this first problem. We're using divergence theorem, right, to turn a flux into a divergence, which is normally how you're going to see it. Not all of the time, but most of the time that's how you're going to see it. Okay, let's look at number 2. Number 2, we've got, well, let me just remind you guys what we have. We've got this guy here, right? So we're going to have f is going to be x plus e to the z, negative 2y, z plus 2. And we're going to let epsilon be the ellipsoid, sorry, where this guy is this, right? We want to find the curl. Okay. Or find the integral of the curl, sorry. So we see integral of curl. So we've got flux of curl means Stoke's theorem, right? So you're like, okay, let's do Stoke's theorem. The issue is that this, okay, the 9 will make it kind of an ellipsoid. So maybe if we're looking, maybe if we're looking here, it's not going to be like this. It's not going to be a sphere, but it'll be maybe something like this. It'll be like this kind, right? This is kind of the shape. It's like a hot dog kind of shape, or like a balloon, right? So this is kind of what we're going to be looking at. It's still closed, right? So what is, if we want to do Stokes, right? We say, our question is, what is our boundary? And here we've got no, the boundary is like the boundary surface, right? But it's a surface encapsulating a solid. It's not a curve encapsulating. It's not something like this, right? Where we've got a curve encapsulating a surface. Like this curve here would be the boundary. No. It's a surface encapsulating a solid, right? So this means that Stoke's theorem is actually not good. You think, okay, well, what do we do then? Well, what we can do is we can say that the integral over epsilon of curl of f dotted ds, this guy is going to be equal to, by divergence theorem, the integral over our solid, so let's call it a balloon, the integral over our balloon of the divergence of curl f dot ds, right? Sorry. This is dv. And so I would be, if we were in class here, I'd be asking, okay, well then what do we think this is? And you guys would start like calculating, and then we'd take like 10 minutes and be like, oh, John, like I'm not sure. But what we have, we've got the power of skipping forward a little bit here, because I assume that you guys have already kind of tried these problems. And you say the divergence of curl, if you ever forget, this is nabla dotted nabla cross f. This guy here is perpendicular to nabla, which means that nabla dot something perpendicular to nabla is going to be 0. That's the kind of heuristic way to remember it. Not that that really is like kind of correct in a rigorous sense, but that's kind of how you want to think of it, is that divergence is nabla dot and curl is nabla cross. So when you do, A dot A cross B, this is going to be 0 because A cross B is perpendicular to A. Anywho, we remember that divergence of curl is always 0, and also curl of divergence is 0, which means that this guy here is going to be a big fat 0. All right. I don't have to wait for questions because nobody's here. But imagine you guys were. Okay, let's go ahead and delete this, and we'll go on to question number 3. And I have to remind myself what question number 3 is. Okay. Epsilon is this guy here. Okay. Epsilon is the solid. Find the volume. Okay, perfect. So how do we find our volume here? Let's look. So we have, that. So we've got, right, so if we do volume is going to be the triple integral. Sorry. Yeah, we'll call it E. Is that what we have? Or epsilon. We've got epsilon of 1 dv, right? And so it'd be really nice to be able to use our divergence theorem here and kind of convert this into something that we can solve a little more easily. So what can we do? Well, we can say that this equals the integral over epsilon of the divergence of call it like 0, 0, d v, right? Because this divergence is clearly going to be 1. And now what we get to do is by divergence theorem, this is going to be equal to the double integral over 0, 0, z dotted with ds over our surface, right? So surface here. Oh, do we have a name for our surface? We'll call it S. Okay. But they've already parameterized it for us, right? So we know that this, oh no. It's not a big deal. It's actually not a big deal. Okay, this guy here, well, now we just do our rules, right? So this is going to be the integral from 0 to 1, integral from 0 to 2 pi of 0, 0, z, but here z is u cubed, dotted with ru cross rv, dv du, right? So we notice that this is actually just going to be the integral 0 to 1, integral 0 to 2 pi of u cubed times ru cross rv in the z component. Right, because we're going to do ru cross rv. This is going to be a vector a, b, c. And then now we do this dot product 0, 0, and it's just u cubed times this z component, right? So what I'm going to do is not compute the whole thing, but instead just compute the z component. So let's do a little note up here. Ru is going to be, if you guys don't remember, let's look back here. Ru will be the u derivative of this, and then Rv will be the v derivative of this. So RU should be, sorry, here we are. RU will be U squared minus U. We've got the derivative of this will be 2U minus 1. Cosine V. We've got 2U minus 1. Sine V. And we've got 3U squared. RV will be negative U squared minus U sine V. This will be U squared minus U cosine V. And this will be 0. Right? And so now we just do our Z component. So our Z component means get rid of this, and just do our cosine squared plus sine squared. This will just end up being 2U minus 1 times U squared minus U. Ooh. Well, let's make it happen. This is dt du, which is going to be the integral 0 to 1, integral 0 to 2 pi of U cubed times. So this cross here will be 2U minus 1, U squared minus U, cosine squared V. And this one here will be plus the same thing. 2U minus 1, U squared minus U, sine squared V. Cosine squared plus sine squared is 1. So this we've got 2U minus 1, U squared minus U, dv du. Okay. And then now I kind of wish I had a little more space here, if I'm being 100. I can do this. Perfect. All right. And so now our final little piece is that, well, the integral from 0 to 2 pi, we can pull all this out. None of this has to depend on v. So this is going to be equal to 2 pi times the integral from 0 to 1 of, let's just pull the u cubed in here so we can FOIL easier. It'll be 2u to the 4th minus u cubed, u squared minus u, du. Okay, and then we can just kind of here, right? So 2 pi 0 to 1. Let's see what we got. Alrighty, we've got 2u to the 6th minus u to the 5th minus 2u to the 5th plus u to the 4th du. You combine these, so this will be 2 pi 0 to 1, 2u to the 6th minus 3u to the 5th plus u to the 4th du. And then you do all your kind of fraction stuff, whatever. We're going to have 2 pi. We're going to have 2/7 u to the 7th, but we plug in u equals 1, minus 1/2, because it's 3/6. So maybe I'll just write 3/6 so we don't get confused. And then plus 1/5 u to the 5th. Right, so this could be u to the 7th, u to the 6th, u to the 5th. But all these are 1 because we're plugging in 1. So this here would be your final answer. There we are. And we notice, if we look at this initial problem, this is like, dude, we have no hope of ever doing this without this trick here. Like, how do you actually find the volume of this? This is insane. But because we've got the parameterization here, you're actually able to find volume really easily. So that's kind of nice. Is that divergence theorem, right? So this can be used to simplify. Maybe we do like a little boop, boop, boop. Copy this guy here. So divergence theorem, right, can be used to simplify flux if it's the flux of a enclosed surface, or it can be used to find volume pretty well. And then here you're just going to do, F equals x 0 0 0 y 0 or 0 0 z, like depending. Right, so if we look at this problem, we saw, okay, well, this u here, like this will give us the best one because, you know, these guys will cancel with the zeros and stuff, and this will be pretty easy to solve because whenever you see something something cosine, something something sine, we assume that this is going to probably like cancel out and give us like cosine squared plus sine squared. You're right, this should be like something that we can do. So you see the cosine and sine, you do it in the last component here. So this guy, we can just look at this cosine and sine one that we did. Okay, and I guess the last one, number 4, is not really much computation that has to be done. Take a minute to think about it, right? We just want to say, can we use this, right? So I'll give you guys a moment to think about this. And then now let's look at it. I assume that you pause the video or something. So C is going to be the circle where Z is 0 and x squared plus y squared is 9, right? So maybe we can draw a little bit. So we are here. We're going to be boom, boom, boom. We're down here on Z equals 0. Right? So we got this circle here of radius 3. And now we're saying, can we use Stoke's theorem to conclude this? Right? Because, okay, so the integral of G dr will be the double integral of the curl using Stoke's theorem. And this guy will just be 0 because we know that curl is 0 here. Right? So you say, okay, well, the integral's 0. Are we happy with this? And the answer should be, no. This is kind of like the example, right? If we just remember 2D, we were doing like Green's theorem or something. It was like, you know, all of your arrows are something like this. And so your curl is clearly like 0 or whatever, but it wasn't defined here. And so you look over here, you're like, oh, what is this line integral? The line integral is clearly positive. But if you do the fundamental theorem or whatever, yeah, the fundamental theorem, we're trying to say it was this conservative or something like this, right? You would see clearly that it was not the case. And the reason, right, is if we look at this guy here, is that this is not defined at 0, 0, 0, which is definitely inside of our curve here. Actually, allow me a moment to consider. XYZ divided by the radius. Getting shorter. So can we do... sorry, just give me a moment here. I'm trying to think if... I mean, surely this is incorrect as written, for sure. Because you can't do this step. This step with Stoke's theorem does not apply because we don't have that. It's defined there. But the question is, could we like change our surfaces, right? So what I'm thinking is like, could we, instead of changing, you know, this is our initial like disk that we're talking about, right? Can we instead look at something that like doesn't contain 0, 0, 0, but has the same like boundary? You know? And so then Stoke's theorem, we can swap and we should actually be fine. I'm trying to think. Okay. Feel free to kind of skip forward in the video if I take too long on this, but I'm kind of trying to figure this out. So we have curl is 0. Maybe not. I have a sense you could, but maybe not. You might have to be careful. All right, so what I'm thinking is like you could say instead we could go the integral over our curve of G dr, right? would really be the integral. Because here we're saying that C, I assume, is that disk. But if we, or S is that disk. But if we call S to be something else, I think this might actually work. Because then you wouldn't encompass that 0, 0, 0, so we wouldn't care about it. Never mind. I don't think that you could. Okay, so this would be no. Like as written, at least that's for sure no. A little thought experiment. I was thinking maybe we could, but maybe not. Okay, and then I was looking at letter B. So we've got let F be this guy right here. You can check the curl of F is 0. Can you conclude this guy here using Stoke's theorem? Okay, what do we think? What do we think? Reckon this one should also be a no because this is this guy here would be defined. So we've got this circle here, right? And now we're talking about the z-axis because now it's not defined when we're on the z-axis. Oh, I see. I apologize. Let me take back everything that I just said. So now we're on the z-axis. Okay. Okay. I was right the first time. I shouldn't have doubted myself. This is a good lesson. You should never doubt yourself, especially on a test or something. Just go with your first instinct. Okay. So the first one is only not defined at 0, 0, 0 at the origin, right? And so as I showed previously, this red here is a shape that has the boundary that does not contain the origin, right? The origin was here, and we kind of went around it. So actually, this first one you could do. You could do this one first. If you define your S properly, and you say that S is not the unit disk, it's something without the 0, 0, 0, then you actually are fine to do this. This one, this reasoning is actually fine. You have to make sure that you define S in the proper way. This one is definitely wrong. You cannot do this because you notice no matter what shape I want to draw, let's see if I try to draw something like this, right? At some point, I have to cross this z-axis. What if I draw something like this as my shape? I have to cross the z-axis, right? So this, this could be your surface here, right? Like, this is fine for S. This has the same boundary curve here. But the issue is that you have to cross the z-axis at some point to make it to this circle here. So to make it to the circle, you have to cross the z-axis, and that means that you have to encompass an undefined point. You have to encompass an undefined point. Whereas this one, the only undefined point is just at the origin, and you can miss the origin if you want. Right? So any of these shapes that I just drew, any of these blue or green or red or whatever, as long as it's not this light blue here, just the circle, you can miss the origin. You can never miss this green z-axis, right? Because this z-axis is going to go forever. We can never miss that. Alrighty, that is all I have for y'all today. I hope that you have a wonderful day. I will catch y'all in the next one. I will see you at the final exam. Take it easy.